In this video, we will see the definition of a ring and few examples. So first we have the definition of a ring. A non-empty set R together with the operations plus and dot is said to be an associative ring if for every AB in R, A plus B belongs to R, which is called closure property with respect to addition. And for every ABC in R, A plus B plus C is A plus B plus C, which is called associativity with respect to plus. And there should exist an element 0 in R such that A plus 0 equals A equals 0 plus A, which is called the existence of additive identity. And for every A in R, see, this must be true for every A in R, and similarly for every A in R, there should exist one minus A in R. There should exist one minus A in R such that A plus minus A equals 0 equals minus A plus A, which is called existence of additive inverse. And for every A comma B in R, A plus B must be equal to B plus A, called commutativity with respect to plus. And for every AB in R, A dot B should belong to R. That's called closure with respect to multiplication. And see, already we had here closure with respect to plus, and here it is closure with respect to multiplication. Now, for every ABC in R, associativity with respect to multiplication, we have to have it as A dot B dot C equals A dot B dot C. And distributive laws, for every ABC in R, we should have A dot B plus C equals A dot B plus A dot C, and A plus B dot C is A dot C plus B dot C. So if we have all these 8 axioms to be true for this R together with this two binary operations plus and dot, then we call that set along with those operations satisfying this axiom, these 8 axioms, to be a ring. Now, if we have in this unit element, that is, for every A in R, 1 into A equals A dot 1. 1 acts as the multiplicative identity, and that is also called unit element. So, if in R we have this to be true, then R is called a ring with unit element. And then commutative ring, when we have A dot B equals B dot A, then we call that ring. This should be true for every AB in R. So in that case, we call R to be a commutative ring. Next, we have these examples. First one is the set of integers under addition and multiplication. The usual addition of integers, usual multiplication of integers. So this forms a commutative ring with the unit element. On the other hand, if we consider the set of even integers only, then also it will form a commutative ring, but it will not have unit element, because 1 is the unit element there that will not be present. So this is just a commutative ring. And the collection of all rational numbers. Collection of all rational numbers under usual addition multiplication of rational numbers is again a commutative ring with the unit element. Similarly, when we consider the collection of all real numbers under addition and multiplication also forms a group, forms a ring, and here usual addition and multiplication of real numbers. And similarly for complex numbers, collection of all complex numbers under usual addition and multiplication of complex numbers forms a commutative ring with unit element. Now we have this special ring. Again, we consider only the set of integers, but addition and multiplication are defined in this way, which we denote as circle plus and circle dot. So if we have the operation A circle plus B as A plus B minus 1 and multiplication A circle dot B as A plus B minus AB, then we can easily check the closure, associativity, and then additive identity. See here, 1 acts as the additive identity. The reason is whenever you have A circle plus some element, that should give back your A. So here A circle plus B is nothing but A plus B minus 1. So this A plus B minus 1 should be equal to A. So this in turn gives, see, our job is to find what this B is. So we have got this one implying that B to be 1. So that is why here we have written A circle plus 1 gives us A back. And similarly here A prime when we consider as the inverse, or you can even write A circle plus B to be 1. So in this case we want to find what is the inverse. So this in turn implies that A plus B minus 1 equal to 1, and this in turn gives B to be 2 minus A. So we have the inverse to be 2 minus A. So if A prime is considered as the inverse, additive inverse of A, then that A prime can only be 2 minus A. Here instead of prime, A prime, we have taken B, that's it. So then commutativity can easily be checked, and because this addition is addition of integers which is commutative, that is why you are getting on the circle plus to be commutative with respect to addition, this circle plus. Again we can easily have the closure property, and distributive this is associativity, and distributive laws can also be checked easily. So we have even the commutativity with respect to circle dot to be true, and so this one, this R, this Z, and this circle plus and circle dot to be a commutative ring. Next we have the collection of all 2 cross 2 matrices where A, B, C, D are real numbers. You can even have it as rational numbers also. Then this is a ring with unit element and is not commutative, because matrix multiplication is not commutative. So in the next section only actually we have the definition of division ring, but here we have an example for division ring. That's why here itself the definition is given. If R is a ring with a unit element, and if for non-zero element A in R, there exists B in R such that A dot B equals 1 equal to B dot A, that is inverse exists for non-zero elements, only commutativity is not there, then in that case you call this to be a division ring. So ring of real quaternions. So this is called a ring of real quaternion. This example, you consider R to be the collection of all elements of this form: alpha naught plus alpha 1I plus alpha 2j plus alpha 3k, where these coefficients, we can call it as, they are from R, the field of real numbers. For x and y in R, we define addition in this way. And this is alpha naught beta naught, then alpha 1 plus beta 1I, and so on. And x dot y is defined in this way. I dot I is quaternion, group of quaternion group that we know, in which we know already that I dot I is taken as minus 1. I dot I is taken as minus 1. J dot j. J dot j is minus 1. Similarly, k dot k is also minus 1. But I dot j is k, j dot I is minus k. And similarly, j dot k is I, but k dot j is minus I. So using this only, quaternion group we have seen already. So this is ring of real quaternions, so in which we make use of this operation. And k dot I is j, whereas I dot k is minus j. So based on that only we have the product being written in this way. So we have again the operation gives us again an element in R only with ijk and this one constant. From 1 and 2, this is 1, this is 1, and this is the second equation. From 1 and 2, we conclude that R is closed with respect to plus n dot, and associativity can be easily checked with respect to plus and similarly with respect to dot. And this one acts as the additive identity, and this one acts as the additive inverse. And this can also be checked, that is commutativity with respect to addition. So, and distributive laws can also be checked. And if we consider 1, which is rewritten as 1 plus 0i plus 0j plus 0k, this will act as the unit element. And for any x non-zero in R, the inverse of that is given by this. So alpha naught minus alpha 1i minus alpha 2j plus alpha 3k upon alpha naught square plus alpha 1 square, alpha 2 square plus alpha 3 square. So this divided by this will act as the inverse. So we have this R under plus n dot to be a ring with unit element, and the non-zero elements have inverse, and this is a division ring. And it can be noted that x dot y is not y dot x. The reason is here your I dot j is k, whereas j dot I is minus k, and similarly for the rest also. So that is why it is not a commutative ring with respect to multiplication. A commutative division ring is a field. So if we have commutativity also to be true, then in that case it will be a field. So for field we have the set of rational numbers under usual addition and multiplication of rational numbers to be a field, and similarly real numbers under usual addition and multiplication, complex numbers under addition and multiplication. See, when we consider the multiplication, it should be remembered that the non-zero elements we'll have to consider. For addition, you can have 0, but when you consider multiplication, non-zero element should form. Non-zero element should have inverse. And another example, finite field, Z7, class 0 to class 6 are the elements of Z7. Addition modulo 7 and multiplication modulo 7, they are described in this way. Then from the table itself we can conclude that it forms, with respect to addition, it will form a group, commutative group, and rather abelian group, and here also. Along with that, distributive laws can be checked. So we have Z7 under addition modulo 7, multiplication modulo 7 to be a group. These operations are already, we are familiar with the group. So in groups itself we have given this to be an example, both under addition as well as under multiplication. So individually from the table we can easily check what are the inverses of each element with respect to addition, and in the same way with respect to multiplication also. That is what is mentioned here. And when we consider Z6, it is not a field, it's just a commutative ring. Of course it has unit element, but it is not a field. With respect to addition modulo 6, from the table we can see that there is no repetition of any column or row. So it's a group under addition modulo 6. But when we come to this multiplication modulo 6, when we consider 3 with 2, multiplication modulo 6, and remember when we consider multiplication, we are not supposed to consider this 0 at all. Non-zero elements only are to be considered as far multiplication is concerned. Only then we can check the inverse, non-zero elements having inverse. So if we consider the multiplication of this element 3 with 2, we get only class 0. And in this row, we don't have We don't have, it's not unique. You have repetition of elements. The elements, if they are not repeated, then we call, in that case we can easily see from the table that it's group we have said. So here it is not so. So it is not a fail. Z6 under addition modulo 6, multiplication modulo 6 is only a completive ring with unit element. It is not a field. So it has unit element. So it is does not form a field, but it is only a ring. So these are the definitions that we have in the first section 3.1 definitions and examples. Thank you.